I'm going to explain you the theorem. If V and W are of dimension M and N respectively over F, then homomorphism of V, W is of dimension Mn over F. That is, here they are given you two vector spaces. They are V and W. And the dimension of V is M and the dimension of W is N. Okay. What they are saying is, we have to prove that the homomorphism of V, W is of dimension Mn over the field F. That is, we are going to prove the dimension of homomorphism of V, W is Mn. Okay, to prove that, what you are doing is, first you are taking some of the basis elements of the vector space V over the field F. Okay, so what you are doing is v1, v2, etc. vm, because v is a vector space of dimension m, right? So that is why you are writing till m, vm. Okay, so let v1, v2, etc. vm be the basis of v over f, and w1, w2, etc. wn, because w is a vector space of dimension n. That is why you are writing till n. Okay, be the basis of W over the field F. Now what you are doing is, you are taking an element from the vector space V, and that element is small v, and we are saying that the element V is of the form this. Okay, this V is of the form this. That is, V is equal to lambda 1 V1 plus lambda 2 V2 plus etc. plus lambda m Vm, where is lambda 1, lambda 2 are the uniquely determined elements. It means the values of lambda 1, lambda 2, etc. lambda m are unique. Okay, that is different. Oh, okay. Okay, we know that this lambda 1, lambda 2, etc. lambda m are the scalars. As we all know that scalars are from the field F, right? Okay. Next, what you are doing is, you are defining something. That is, you are defining two things. First, you are defining a map. Okay, after that you are defining a condition. Okay, so have a look at this. You are define Tij from V to W, that is from vector space V to W, by V Tij is equal to lambda I Wj, where I is equal to 1 to etc. m and j is equal to 1 to etc. n, and take Vk Tij is equal to, if k, this the suffix of V and the suffix of I, a suffix of t, that is this I. If k and I are different values, then you have to put 0. If the suffix k and I are equal, then you have to put wj. What wj? This value. W with this suffix, this value. Okay, here you have j, so you are putting j here. So this is how you are defining. Now what you are going to do is, this mapping Tij, you will prove that this mapping Tij is a homomorphism. To say it is a homomorphism, there are two conditions. If the two conditions are satisfied, then you can say that mapping as a homomorphism, right? So here that is what you are going to say. To prove Tij is a homomorphism, that is, to prove these two conditions should be satisfied. That is, V plus W into Tij is equal to Vtij plus Wtij, and alpha V of Tij is equal to alpha into Vtij. These are the two conditions of homomorphism. So now what you are doing is, you are having VW, all these things here, right? So this V and W are the elements you are taken from the vector space capital V. Then V is of the form this and W is of the form this. V is equal to lambda 1 V1 plus lambda 2 V2 plus etc. plus lambda m Vm. W is equal to mu 1 V1 plus mu 2 V2 plus etc. mu m Vm. Okay. Now you are going to consider the left hand side of the first condition of homomorphism. So for that, you first, before considering this, what you are doing is, you are finding the value of V plus W first. So that is what you are doing here. V plus W is equal to, you will get this value. This is V and this is W, and finally you get this. Now you are considering the left hand side of the first condition of homomorphism, that is v plus w into Tij is equal to, okay, you are what you are doing, v plus w into Tij plus this term into Tij plus etc plus this term into Tij, right? That is how you are writing. In between you are writing the ith term also. Now after that all the other terms will become 0 except the ith term. The reason is because if you look at this v1 Tij, the suffix of v is 1 and here this is I. That is, this and this value are different. If this and this value are different, then what we have to do? If this and this value are different, what we have to do? We have to put 0. So like that, all the other terms will become 0. Only ith terms will be there. So you are writing the ith term. Lambda I wj plus mu I wj. So from this you are writing this lambda I as it is. In the place of wj, you are writing like this. If wj means bk Tij here. So here what you will do, vi Tij and write plus this mu I. In the place of wj you are writing vi Tij again. Okay, now v Tij, how you are writing this? How you are? I will tell you how you are writing this. Consider this. This is lambda I, right? That is, you are using this here. Consider this is lambda I, and this, consider this two elements as wj. Okay, so that how can you write v into Tij, right? That is what this condition says to us. So that is how you are writing vi Tij here plus here you are writing w Tij. To show the variation you are writing in that format, but you are using two. You are writing in the place of here you are writing v and here you are writing w. That's the only difference. Now the first condition of the homomorphism is satisfied, and this is the second condition. Consider the left hand side, alpha v of Tij is equal to alpha lambda I wj. That is, you have to consider this is v and this is Tij. Okay, v Tij means you can write from our condition, we have v into Tij is equal to lambda I wj. Okay, so that is how you are writing. Am I right? Yes. Wj. In the place of lambda I, you are writing alpha lambda I. Because here with this v, we have alpha, right? We could not leave this alpha alone. Because you have, here you have alpha v, here you have only v. Right, so if there is only v, then you put alpha lambda I wj. If here is alpha v means you put alpha with this lambda I. So that is how we are writing. Alpha of lambda I into wj. Put this bracket to these two in this step, and after that alpha of lambda in the place of wj you are putting vi Tij, and alpha of here lambda I wj format. So how can you write? V Tij. So that is how you are writing. So finally you proved the second condition of homomorphism also. Thus Tij is a homomorphism and hence Tij belongs to. So if two conditions of homomorphism are satisfied, then you can say this Tij, our mapping Tij belongs to homomorphism of v, w. Now you are going to say that Tij form a basis of homomorphism of v, w over f. It form a basis. To say that, you have to prove the condition vis not equal to vis. Okay, so first what you are doing is, first you are going to dealing with the right hand side. That is, here you have s, right? So first you have to choose this s. Take an element s from the homomorphism of v, w, right? So that is why you are let s belongs to homomorphism of v, w. Now again here we have vi of s. So before writing the ith term, you are writing the first term. Let v1 is equal to this. You are assuming by your own. There is no nowhere that you have to choose like that. So V1 is equal to alpha 11 W1 plus alpha 12 W2 plus etc. alpha 1 and W1. For some, this alpha 1 and alpha 1 to etc. all are belongs to the field F. In general, so in the here V1s, so like that you can write V2s, V3s. So in general, you are writing VIs. So here in the place of here you put I, right? Because in each term, in each times, this is the value that is going to vary, right? So that is why when you are writing the ith value, you will write ith value, you will write like this. So alpha I1 W1 plus alpha I2 W2 plus etc. alpha IN WN. Now you have finally you came to one conclusion about what is the value of VIS. Now you have to say what is VIS not, right? So before that, you are assuming giving a value for S naught, that is, let S naught equal to alpha 11 T11 plus alpha 12 T12 plus etc. alpha 1n T1n and alpha 21 T21 plus alpha 22 T22 plus etc. alpha 2n T2n etc. This is the ith term, and finally Mn. Now you are finding VI S naught. This is very easy. Put that VI and write the S naught values again here. And all the other values get cancelled except the ith values. So write the ith values. From this you are multiplying VI inside so that you get this line. And after that V1 Ti1, right? So here the suffix of V is I, is also I. So both are same. If it is same, you put W and this value. So 1. Here these values are same, so you put W2. Similarly, you are writing to all. So finally you get VIS not equal to VIS. This is the VIS value, right? So you get this. So VI get cancelled. You get S equal to S naught. So we know that this S naught is a linear combination. This is a linear combination. These elements are linear combinations, right? So that is why your S naught is linear combination. So you are getting here S naught equal to S. So you can say S must be also same linear combination. Therefore you can say Tij form a basis of homomorphism of V, W over the field F. Now we are saying that Mn elements of Tij is linearly independent. Okay, this is what the next part you are going to prove. Mn elements of Tij is linearly independent. I equal to 1, 2, 3, etc. M and J is equal to 1, 2, 3. So consider this, and you are finding Vk of you are writing this. Okay, this is not difficult. There you have wrote with alpha, and here you are writing with beta. That is the only difference. Here you are writing the ith term, and here you don't write that ith term. Here you will write the kth term in between. So that is the only difference. Now you write Vk of this term is equal to 0. Okay, so this equal to, you will consider this equal to 0. Therefore when you multiply Vk with this, is equal to 0. Now all the other terms will be cancelled. Only the kth terms will be there. So Vk of this value. So from this you are multiplying the same way that you have done for in the previous part, right? Just the same way. There is here you have nothing to feel difficult. So you will get this. Since W1 here you have W1, W2, etc. all these things, right? These are linearly independent. Okay, so that is why you can say Bk1 equal to 0, Bk2 equal to 0 and Bkn equal to 0. So from this you can 1, 2, 3, the values are varying. So for varying values you can put J in general. So Bkg is J equal to 0 in the place of J will be 1, 2, 3 till n. So we have I equal to k, right? So that is why you are writing the place of k you are putting I. So beta I j is equal to 0. So thus finally you can say Mn elements of Tij. If beta ij is equal to 0, if these elements are 0, then you can say this Tij is linearly independent over the field F. They form a basis, therefore they form a basis of homomorphism of V, W. Thus finally you have proved that homomorphism of V, W is of dimension Mn over the field F. Hence the proof.